Hi friends, today we are going to learn engineering disasters. Welcome to Invention and Discovery, where we explore the ideas, inventions, scientific breakthroughs, and engineering achievements that changed our world, and sometimes taught humanity its most valuable lessons. Imagine a machine capable of producing enough electricity to power an entire city. Now imagine that same machine becoming the site of the worst accident in the history of commercial nuclear power. On April 26, 1986, at exactly 1:23 a.m., Reactor No. 4 at the Chernobyl Nuclear Power Plant suffered a catastrophic accident during what was supposed to be a routine safety test. Within seconds, explosions destroyed the reactor building. A fire burned for days. Radioactive materials spread across large parts of Europe. More than 350,000 people would eventually be evacuated or permanently relocated. The city built to support the plant would become a ghost town almost overnight. But what exactly happened? Why did one reactor fail so catastrophically? And how did this single event change nuclear engineering forever? Let's begin at the beginning. The Chernobyl Nuclear Power Plant was located in the northern part of what was then the Ukrainian Soviet Socialist Republic, about 110 kilometers north of Kiev and roughly 10 kilometers south of the border with Belarus. Construction began in the early 1970s as part of the Soviet Union's ambitious nuclear power program. The complex eventually included 4 operational RBMK, 1,000 nuclear reactors, while 2 additional reactors were still under construction when the accident occurred. Next to the plant, engineers created an artificial cooling reservoir covering approximately 22 square kilometers, providing the enormous amount of water required for reactor cooling. Just 3 kilometers away stood the modern city of Pripyat. Founded in 1970, Pripyat was built specifically for power plant workers and their families. It was considered one of the most modern cities in the Soviet Union, complete with schools, hospitals, parks, supermarkets, sports facilities, and apartment buildings. By 1986, nearly 49,000 people called Pripyat home. Most believed they were living in one of the safest and most technologically advanced communities in the country. The power station itself played an important role in supplying electricity across the Soviet Union. Each reactor could generate approximately 1,000 megawatts of electricity, enough to power hundreds of thousands of homes and industries. To many engineers, Chernobyl represented progress. It demonstrated humanity's ability to harness the incredible energy locked inside atoms. But to understand why the accident happened, we first need to understand how the reactor worked. Every nuclear power plant begins with one scientific principle: nuclear fission. When the nucleus of a uranium atom absorbs a neutron, it becomes unstable and splits into smaller atoms. That process releases an enormous amount of heat, along with additional neutrons. Those neutrons strike other uranium atoms. More atoms split. A carefully controlled chain reaction begins. Instead of using fire to boil water, a nuclear reactor uses this heat from fission. The steam produced spins giant turbines connected to electrical generators, producing electricity for homes, hospitals, schools, and factories. The reactor used at Chernobyl was called the RBMK-1000, a Soviet-designed reactor unlike most Western designs. It used slightly enriched uranium dioxide fuel, containing about 2% uranium-235. Large blocks of graphite surrounded the fuel. Their job was to slow down neutrons, making the nuclear chain reaction more efficient. Ordinary water flowed through more than 1,600 pressure tubes surrounding the fuel. The water absorbed heat, turned into steam, and drove 2 massive 500-megawatt turbines. Combined, the reactor produced around 1,000 megawatts of electricity. One major advantage of the RBMK design was that operators could replace fuel while the reactor remained in operation. This reduced downtime and increased electricity production. However, the design also contained characteristics that required careful operation. One of the most important was something engineers call a positive void coefficient. That sounds complicated, but the idea is surprisingly simple. Normally, if cooling water decreases inside many reactor designs, the nuclear reaction slows down. The RBMK could behave differently. Under certain operating conditions, when water turned into steam bubbles, called voids, the nuclear reaction could actually become stronger. More steam could mean more power. More power produced more steam. That created a dangerous positive feedback loop. Another important feature involved the reactor's 211 control rods. These rods were designed to absorb neutrons and slow the nuclear reaction during normal operation or shut the reactor down during an emergency. However, the original RBMK control rods contained graphite tips. During the first moments of insertion, those graphite tips displaced cooling water before the neutron-absorbing sections entered the core. Under very specific conditions, this could briefly increase reactor power instead of reducing it. Engineers later recognized that this design characteristic contributed significantly to the events of April 26, 1986. By itself, the reactor was not destined to fail. But when these engineering characteristics combined with procedural decisions during an unusual safety test, the consequences became catastrophic. By the evening of April 25, 1986, Reactor No. 4 was scheduled for a routine shutdown. Before shutting it down, engineers planned a safety experiment. The objective was simple. If the plant suddenly lost external electricity, could the spinning turbine continue generating enough power for a few seconds to keep the cooling pumps running until the emergency diesel generator started? It was a reasonable engineering question. A similar test had been attempted the previous year, but it had not produced the desired results. This time, the team hoped to gather better data using an improved voltage regulator. However, events did not go as planned. Electricity demand on the Soviet power grid delayed the reactor shutdown for several hours. When permission was finally given to reduce power, the reactor had already been operating under unusual conditions. During the shutdown process, the reactor's power unexpectedly dropped to nearly zero. To recover, operators withdrew many of the control rods beyond normal operating limits. Several automatic protection systems were also disabled so the experiment could continue. These actions placed the reactor in an unstable condition. Pause. At 1:23 a.m. on April 26, the test began. Steam to the turbines was reduced. As the turbines slowed, water flow through the reactor changed. Steam bubbles, known as voids, formed inside the cooling channels. Because of the RBMK reactor's positive void coefficient, reactor power began increasing instead of decreasing. Recognizing the unstable conditions, the operators pressed the emergency shutdown button, known as AZ5. It was designed to stop the nuclear chain reaction immediately. But because of the graphite-tipped control rods, their initial insertion briefly increased reactivity inside parts of the reactor core. Within seconds, power surged to many times the reactor's normal operating level. Fuel channels ruptured. Water instantly turned to steam. A massive steam explosion lifted the 1,000-ton upper biological shield from the reactor. A second explosion followed moments later, likely involving hydrogen and other gases produced during the accident. The reactor building was destroyed. Burning graphite and nuclear fuel were thrown into the open air. The world's worst commercial nuclear power plant accident had begun. The explosions killed 2 workers during the accident itself. Firefighters from nearby Pripyat arrived within minutes, unaware that the burning debris around them contained highly radioactive material. They fought the fires with extraordinary courage, believing they were responding to an ordinary industrial fire. Many received extremely high doses of radiation. Within the following weeks, 28 emergency workers and plant personnel died from acute radiation syndrome, while many others required intensive medical treatment. The reactor continued releasing radioactive materials into the atmosphere for approximately 10 days. Among the most significant radioactive substances released were iodine-131, with a half-life of about 8 days, and cesium-137, which has a half-life of around 30 years. These materials spread across Ukraine, Belarus, Russia, and were detected in many parts of Europe, including Sweden, where unusually high radiation levels first alerted the international community that a major nuclear accident had occurred. The city of Pripyat was evacuated on April 27, 1986, about 36 hours after the explosion. Nearly 49,000 residents left believing they would return within a few days. Most never did. By May 14th, approximately 116,000 people had been evacuated from the surrounding 30-kilometer zone. In the years that followed, another 220,000 people were permanently relocated, bringing the total number of evacuees and resettled residents to around 350,000. Cleaning up the disaster required one of the largest emergency operations in history. More than 600,000 soldiers, engineers, miners, firefighters, doctors, pilots, and volunteers, later known as the liquidators, helped contain the reactor, remove contaminated debris, and construct the first concrete shelter over Reactor No. 4. Their work greatly reduced further radioactive releases and made it possible to stabilize the site. The environmental impact of Chernobyl was enormous. Large areas of land became contaminated, leading to the creation of the Chernobyl exclusion zone, which today covers approximately 4,300 square kilometers. Although people were forced to leave, wildlife has gradually returned to many parts of the region, making it an unexpected area of scientific research into ecosystems with limited human activity. The health effects have been studied for decades. According to the United Nations Scientific Committee on the Effects of Atomic Radiation, the clearest long-term health consequence has been an increase in thyroid cancer among people who were children or adolescents at the time of the accident due to exposure to radioactive iodine. Thousands of cases have been documented, and most were successfully treated when diagnosed early. Scientists continue monitoring the long-term effects, while many studies have found no evidence of a major public health impact in the general population beyond those directly exposed. Although research continues and uncertainties remain, perhaps Chernobyl's greatest legacy lies in engineering. The accident exposed weaknesses in reactor design, operating procedures, emergency preparedness, and organizational safety culture. Following the disaster, RBMK reactors underwent significant safety modifications. Control rod designs were improved. Operating rules became stricter. International cooperation between nuclear organizations expanded dramatically. Countries adopted stronger safety standards, shared operational experience more openly, and strengthened independent regulatory oversight. In many ways, Chernobyl transformed how the global nuclear industry approaches safety. Chernobyl is remembered as one of history's greatest engineering disasters. But it is also remembered as one of engineering's greatest teachers. The accident demonstrated that even the most advanced technology demands constant vigilance, rigorous testing, transparent communication, and a culture where safety always comes before production. Every invention has the potential to improve lives, but every powerful invention also carries responsibility. The true measure of innovation is not only what we create, but how carefully we understand its risks, learn from our mistakes, and protect future generations. More than 3 decades later, the lessons of Chernobyl continue to influence reactor design, emergency planning, scientific research, and international cooperation around the world. Its story reminds us that progress and responsibility must always move forward together. Thank you for joining me on this journey through one of history's most important engineering events. Subscribe for more stories,